many terms, and we have as subsets monomials, binomials, trinomials, etc. So we shall be looking at the algebraic expansion of binomials, two-termed polynomials. And we will not delve too detailed into that because this is a revision show. And we shall be looking at a few concepts. So keep this definition in mind. It is the algebraic expansion of powers of a binomial. So there will be binomials and there will be exponents or powers. And we shall be investigating how do we expand those binomials to the exponent or powers given. We'll learn a few techniques together. And once again, I encourage you to participate. You never learn how to drive by simply watching people drive. You will learn to drive by getting behind the wheels and making a few mistakes in the process. I hope they don't become too dangerous mistakes, but that's how to learn. You will not learn by simply following with your eyes. You would have to write. So I encourage you, get yourself a notebook, a pen or a pencil, and a calculator will be very, very handy for this. The calculator on your phone may not be as handy. Well, you could give it a shot nevertheless. So let's go. What are the key concepts in this topic? Key concepts, polynomials. Well, we said the polynomials are just many terms. That's why it's polynomial, like polythene, many Athens, polytechnic, many techniques, polygamous, many marriages. So polynomials, many terms. Tonight, we shall be focusing on binomials, two terms. Another very important concept for tonight will be the expansion, of course. If you remember our definition, we said that the binomial theorem is the algebraic expansion of the powers of a binomial. And especially, we shall be considering an important technique in expansion using what we call the Pascal's triangle. Well, it gets its name from the popular and very renowned French mathematician Blaise Pascal. And we shall look at the factorial, something you would enjoy if you haven't known it before. If you know it already, it's a good time to smile when you see it in operation. And finally, we shall look at combination. Yeah, if you're fashion inclined, you're thinking of combination, what colors match what colors. But this time around, it's not in that sense, it's in a different sense. So let's begin with expansion. Now, before then, we had the problem of the day, and I guess you may have tried it. We had this problem of the day. We said expand 1 plus x to the power 12 in ascending powers of x up to the 5th term. And the second part of that question says a sum of p cities invested at R% compound interest amounts to p, the expression in parentheses 1 plus r exponent r on 100 all exponent n after n years. Using the binomial expansion in BI, estimate correct to the nearest 1,000 cities how much 50,000 old Ghanaian cities will amount to at 7% compound interest after 12 years. This question is an SSSCE July 2004 question 9B. That was our problem for the day. There was a second problem for the day, and we said write down the first 4 terms of the binomial expansion of 1 minus x to the power half. And the second part of the question says to use your expansion in I above to evaluate the square root of 15 correct to 3 decimal places. An SSSCE November 2003 question from 9B. You would notice very interestingly that they are both question 9s and 9Bs. Remember the structure of our exams. Any question from question 9 to question 15 will be optional questions earning you 13 marks if you get the full question right. And typically, because this is question 9, it is a pure math question. Well, we shall solve this question subsequently, but let's go into that. By the way, you could grab a phone, and when we open the phone lines, you'll have an opportunity to call on 0302-211-698 and 0302-211-699. I repeat the numbers, 0302-211-698 and 0302-211-699. Now, on your screen, you have expansions of the binomial x plus 1 from power 0 all the way to 6. Ordinarily, you can do this by simply saying, for example, x plus 1 to the power 2. You will say x plus 1 multiplied by x plus 1, and you will distribute one binomial over the second. So x multiplying x plus 1 plus 1 multiplying x plus 1. You have 4 terms. You simplify it, and you end up having x squared plus 2x plus 1. I have just ticked that part of the question. Now, if you kept doing that, you would notice that you have quite a lot of work to do. As the powers increase, you have an expanded outcome. So, for example, x to the power 2, you would notice you have 3 terms. X squared plus 2x plus 1. 3 terms. When you have x plus 1 to the power 3, and you expand and simplify, you would have 4 terms. X to the power 3, 3x to the power 2, 3x this time around to the power 1, and 1. 4 terms. I need you to note these things. Now, let me pause here to give a few comments. We shall look at that expansion. This show is targeted at you final year students in particular. If you are in your first or second year, it's a good time to have a handle on this. But if you're in your final year, we want to remind you of a number of things. We want to firm your grip on key concepts. We want you to exercise your wits, and that's the reason for problem of the day. But more importantly, and very, very importantly, we want to point out very specific tripping points. There are points students stumble at, and we want you to avoid that. It will be very costly to trip at that same point. And so we shall be emphasizing, I shall be emphasizing areas you should look at and look at very carefully. So let's get back to our expansion. Now note this. Now let's begin with the expansion. For a minute, I want you to ignore x plus 1 to the power 0, which is the very first. Look at x plus 1 to the power 1. How many terms do we have there? 2 of them. X and 1. When we have x plus 1 to the power 2, we had 3 terms. X squared, 2x, 1. When we have x plus 1 to the power 3, or exponent 3, we have 4 terms. X cubed, 3x squared, 3x, and 1. When we have x plus 1 to the power 4, you notice how many terms? I want you to count. All right, you notice we have 5 terms. Look at x plus 1 to the power 5. How many terms do we have? X to the power 5, 5x to the power 4, 10x to the power 3, 10x to the power 2, 5x, and 1. 6 terms. Now, I love math because it's predictable. In fact, Even things that are not supposed to be predictable, we try to make them predictable. So we study probabilities. We like to make things predictable. X plus 1 to the power 6, you can predict how many terms there will be. Indeed, even if I said x plus 1 to the power 40, without manually expanding and simplifying, you can tell how many terms there would be. X plus 1 to the power 40 would have, you guess, 41 terms. So no matter the exponent, especially if it is a whole number, positive whole number that is, the number of terms would increase by 1. All right, now let's do a little modification of what we have. You notice the same thing has been arranged, but this time around we seem to have rearranged it so that it looks like a geometrical shape. It looks triangular. Well, what is it about this triangle? If you recall, if you joined us much earlier, you will recall we mentioned Pascal's triangle. Well, we're about forming that. So let's make it a lot more clearer. Notice something very specific here. I have made the coefficients of each term red. And that is to draw your attention to something. So x plus 1 to the power 0 is 1, because we know that so long as you have a non-zero number and it is raised to the power 0, your result should be 1, so long as it's a non-zero number. All right, now look at x plus 1 to the power 1. Ordinarily, and in fact a while ago you saw it written as x plus 1. But I have written this time around 1x plus 1. And I have repeated the same 1x in all of the other expansions from 0 to 6. Well, it's just for effect, just to draw your attention to something very important. Ordinarily, we do not write the 1 because it's taken for granted that if I said x squared, you know I mean 1x squared. I have taken the liberty of introducing the 1 to show you that there is an interesting pattern, and that pattern was made quite popular by the French mathematician Blaise Pascal. Very astute man. Now he observed, and I want you to observe as well, that assume that you had zeros on each side of the 1. You could actually form an endless infinite number of coefficients of the expansion of x plus 1. So now let's look at it. Assume that on each side of the 1 there is a 0. Add the 0 on the left to 1, you notice you have the 1 below. So for example, if we had a 0 here and a 0 somewhere there, and we added 0 to 1, we will get the 1 below there, 1x. If we added the 1 on the 0 on the right of the 1, I don't know if it's right or left depending on how you're looking at it, 0 plus 1, we'll get another 1. If we came downwards and we did the same for the second level, 0 there and 0 here, you would notice if we added 0 to 1, we get the 1 below it. Now, we do not have only zeros, we have 1 and 1. If you added 1 to 1, you notice you get the 2 below. If you added 1 to the 0 on the right, you get 1. So we have 1, 2, 1. Okay, assume there is another 0 there and a 0 here. Let's add again. 0 plus 1. You notice you have the 1 below. 1 plus 2. You got 3 down. 2 plus 1, another 3 down, 1 plus 0, you have 1. Should I take that again? Sure, I will. Let's go back. 0 plus 1 from the very beginning. So I am assuming there are zeros. If there are no zeros, it's as good as saying just repeat 1 downwards. So 0 plus 1, 1. 1 plus 0, 1. I assume There are two zeros on the second level. 0 plus 1, 1. 1 plus 1, 2. 1 plus 0, 1. Another set of zeros on the sides. 0 plus 1, 1. 1 plus 2, 3. 2 plus 1, 3. 1 plus 0, 1. So I have 1, 3, 3, 1. If I assumed again that there's another 0 there and another 0 here, let's go through the process again. 0 plus 1, 1. 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. 1 plus 0, 1. So I have 1, 4, 6, 4, 1. And we could continue infinitely. You would notice 1 plus 4 gives us 5. 4 plus 6 gives us 10. 6 plus 4 gives us 10. 4 plus 1 gives us 5. And 1 is repeated again. The last one line, 1 plus 5, 6, 5 plus 10, 15, 10, 10, 20, 10 plus 5, 15, 5 plus 1, 6, 6 plus 1, 5 plus 1, 6, and 1 plus 0, 1. And we could continue on and on and on. Now, this forms a triangle we refer to as Pascal's triangle. What do we use it for? Using the Pascal's triangle, you could indeed expand any number. So for example, if you were required to find x plus 1 to the power 4, instead of multiplying x plus 1 by another x plus 1 and multiplying that by another x plus 1, and when you have done multiplying for the third time, you do again, so that you have x plus 1 in 4 places, which is quite laborious. All you needed to do was to remember the coefficients 1, 4, 6, 4, 1. If you wrote them out and did a few things I'll show you shortly, you should be able to expand the same thing. But let me test you a bit, and it would be great if you called in to tell me what your answer was. I want you to attempt expanding this, x plus 1 to the power 7. Try it. Remember the last thing we had? We had 1, 5, 10, 10, 5, 1. And then we had 1, 6, 15, 20, 15, 1. 15, 6, 1. All right, so try x plus 1 to the power 7. Since you got the question, while you try it, let me take you one step backwards. Let's look at something together. Just something to note. Did you notice if you tried folding this triangle from the base? So this time around, our base would be 1, 6, 15, 20, 15, 6, 1. If you held 1, 1 as your tip and you tried folding it, you would notice a very interesting symmetry. Now watch this. From the very bottom, you have 1, 1. So left, right, 1, 1. When you come a little closer, you have 6, 6. And when you come even closer, you have 15, 15. And then you have 20. If you moved higher or upper, you would have on extreme ends 1, 1. If you move closer, 5, 5. And then you have 10, 10. Let's go even one step higher. You get 1, 1, 4, 4, and 6. Let's go even higher. 1, 1, 3, 3. So you notice that in the Pascal triangle, you have a symmetry. So either way, you're going to have 1 on both sides. And then as you come closer and closer, the values repeat themselves. And that's a beautiful symmetry. All right, so let's get back to our question. Now that you know that x plus 1 to the power 6 gives us 1, 6, 15, 20, 1561. What about x plus 1 to the power 7? It'll be great to call in to tell me what your answer is. But before you do that, so let's verify, just so that you're a little more confident. You have x to the power 7, or 1x to the power 7, plus 7x to the power 6, plus 21x to the power 5, plus 35x to the power 4, plus 35x to the power 3, plus 21x to the power 2, plus 7x plus 1. Did you notice the symmetry once again? That we have 1, 1, 7, 7, 21, 21, 35, 35. One more thing to note, and that almost skipped me. Did you notice that the powers of x keep decreasing? So you have, in this case, x to the power 7, the first term, the next term, x to the power 6, x to the power 5, to the power 4, to the power 3, until you get to 1, where in effect, or really and truly, it is x to the power 0, only we don't write it. So that is something interesting to note, that in this particular instance, we have, or just like the previous ones, we have expanded x plus 1 in descending powers of x. It is something to please note, and I encourage you, please note it. In the questions, especially the problem of the day, you would notice there was a specific instruction, and we are particular when it comes to math. When you're required to expand something in ascending powers, if you do it in descending powers, your final answer might be the same, but because you've ignored the rules, you might lose a mark or sometimes all of it, and that's quite painful. So please be very conscientious, be very careful. All right, so there is another one to try. X plus 1 to the power 8. You can take a cue from x plus 1 to the power 7. And notice also that so far we have only expanded x plus 1. You could expand x plus 2, x plus 3, anything really. And I'll show you the technique as we go ahead. So give it a try. X plus 1 to the power 8. What do you have? Give it a shot. All right, so I need you to call in. Let's be sure that together we're getting the answers. If you have a phone by your side, or you can get someone to call for you, 0302-211-698, 0302-211-699. Call in and tell me. Okay, so our lines have changed, and you pardon me for that. 0302-211-705 and 0302-706. So pardon me for that. 0302-211-705 and 0302-211-706. I want to know, what do you have for x plus 1 to the power 8? We have expanded x plus 1 from 0 all the way to 6 and even to 7. Let me know what you have as x plus 1 to the power 8. 0302-211-705, 0302-211-706. X plus 1 to the power 8. Well, while we await our first caller, like I said, make the observations, and it is not sufficient to look. It is a lot better to see. Ernest, good evening.
Evening.
Yes, Ernest, you're welcome to the show. How are you doing tonight?
I'm doing great.
Good. Ernest, are you a student?
No.
Okay. So, well, you're welcome to the show anyway. So, Ernest, tell me, what do you have for your expansion? I guess you gave it a try.
Yeah.
Okay, so Ernest, let me hear you.
1x to the power 8.
Okay.
8x to the power 7.
All right.
28 to the power 6.
Yep.
56 to the power 5.
All right.
70 to the power 4.
All right.
56 to the power 3.
Yep.
28 to the power 2.
Okay.
8 to the power 1.
All right.
And 1.
Ernest, you are fantastic. You're fantastic. Ghana, West Africa, give it up for Ernest. Ernest, that was correct. And that's just as precise as it is. So, those are the answers Ernest has. Ernest, thank you very much for calling from Kumasi. We are grateful. We have another question there. This time around, deliberately, we have skipped x plus 1 to the power 9. We went all the way to x plus 1 to the power 10. And that's just to wake you up a little more. So somebody try that for me. X plus 1 to the power 10. In other words, you must conquer x plus 1 to the power 9 first. Or if you know your way around this, you should be able to do this rather quickly. Ernest helped us from Kumasi. Thank you, Osekrum. Rebecca, good evening. You're calling from Aguna Swedro. Did I lose Rebecca? Oh, sorry, Rebecca. Please try again. And I'm happy, Becky, you're calling. All right. So x plus 1 to the power 10. Who is helping us? Recall, all you needed to do was to get your coefficients from Pascal's triangle. I have somebody from Kumasi. Is that Gideon? David, good evening.
Good evening.
You're welcome to the show, David.
Thank you.
How are you tonight?
I'm good.
And I am also very fantastic. Are you a student, David?
Yes, I'm a student.
What school, if I may?
Factorial.
Oh, fantastic, was. Fantastic. So, David, tell me, x plus 1 to the power 10, what do you have as your expansion?
Yeah. 1x to the power 10.
Yes.
Plus 9x to the power 9. Plus 36x to the power 7.
Okay, so David, I want you to pause 1 minute. Look at the question on your screen. It is x plus 1 to the power 10. The last question we resolved, that Ernest helped us resolve, was x plus 1 to the power 8. So you notice there is something you are missing out. Don't you see that? Hello, David. You notice you're skipping something, right?
Yes.
All right,
yes.
so come back again. Try again. Try again. Try again.
Right.
All right. While David is trying to sort that out, and he skipped something important. Notice the power, the exponent is 10. So there's a little more challenge there. In other words, you have to conquer an intermediary expansion before you can do this, unless you know another trick, which I shall be showing to every other person in the course of this show. So who is helping us? X plus 1 to the power 10. 0302 211 705 0302 211 706. Let me hear you. Rebecca, you can call back. You call from Aguna Swedro. David, if you're sorting yourself out and you have sorted yourself out, let me hear you. You'll be our second caller from Kumasi. X plus 1 to the power 10. All right. This is stretching us. That is why it's called further math or elective math or additional math. It stretches you a little further. But it's not too much for you to do. Even if you're not an elective math student, you can give it a shot. Only if you did it the traditional way, it will cost you a lot of time. You will still get the answer, but it will cost you a lot. Because in grouping like terms, it will be quite challenging. I have Joseph Watson from Asante Mampong. Good evening.
Good evening.
You're welcome to the show, Joseph.
Okay, thank you.
I am fine. How are you?
I'm also fine, please.
Fantastic. You're a student, I suppose?
Yes, please.
What school, if I may ask?
Kumasi Anglican.
Oh, Kumaka, you're welcome to the show.
No, Kumasi Anglican.
Oh, sorry, Cass. You're welcome. You're welcome to the show.
Thank you.
Are you in your final year?
Yes, please.
All right. So, Joseph, what is the expansion of x plus 1 to the power 10?
Okay. We have X.
Oh, too bad. Rebecca, you're back.
Yeah, I'm back.
You are welcome.
Thank you.
So, how is Aguna Swedro today?
Everything is ongoing.
Okay, that's beautiful. So, are you a student, if I may ask?
Yeah.
What school?
Yakrom Senior High.
I did not get that.
Yakrom Senior High.
All right. Now, so tell me, did you succeed? Did you succeed in expanding x plus 1 to the power 10?
Yeah, sure.
So let me hear you.
Okay. X raised to the power 10
Okay.
plus 10 raised to the power 9
Fantastic.
plus 45 raised to the power 8
Okay.
plus 120 raised to the power plus 120 x raised to the power 7
All right.
plus 210 x raised to the power 6
Okay.
plus 252 x raised to the power 5
Wow.
plus 210 x raised to the power 4
Okay.
plus 120 x raised to the power 3
Okay.
plus 45 x raised to the power 2
All right.
plus 10x plus 1.
Rebecca, I am
Yeah.
applauding you for even the courage to try it. That was a good one. But now tell me something, Rebecca, if you can hang on. What did you notice about your expansion? Did you notice something?
Yeah, I noticed something.
So let me hear you.
Looking at the first number and the last number.
Okay.
You see, the first number was 1, x raised to the power 10.
Yeah.
And the last number 2 was 1.
All right.
And the second number was 10.
Okay.
Yeah. And the last but one number was 10.
All right.
And looking at the third one, it was 45 x raised to the power 8.
Okay.
So the last but 2, it was 45 x raised to the power 2. So the numbers were equal; they were corresponding.
Fantastic, and I like your use of the word corresponding. So you notice there is a symmetry of numbers.
Yeah.
Fantastic.
Yes,
yeah. So you could actually expand any set of numbers so long as the power is a whole number and it is not a fraction. All right. So Rebecca, do you notice also that the powers of 10 are decreasing? 10, 9,
yes,
8.
They are decreasing. First one it was 10, and the second one it reduced to 9.
All right.
The third one it reduced to 8.
Okay.
The fourth one, yeah.
Okay. So, but what do you notice about the last x? What do you have there? You have 10x, right?
Yeah, 10x.
So it reduced from 2 to 1. Then what happened? Why is there no 0?
Why is there no 0?
Why don't we have x to the power 0?
Because any number raised to the power 0, raised to the power 0 is 1.
And you are right.
Definitely, x
Yeah.
raised to the power 0 is 1. That's why we have that one there.
All right, and that is why we do not write it.
Yeah.
All right, but just a little word of caution for precision's sake.
Okay.
We do not say that any number raised to the power 0 is 1, because
Okay.
if you raise 0 to 0, you won't get 1.
Okay.
All right. Any non-zero number to the power 0
Okay.
will yield 1. Thank you very much, Rebecca, and
No.
I am applauding you for that excellent job. Thank you very much. All right, so viewers, we have been able to demolish x plus 1 from powers 0 all the way to 10. Now, let's go into a few more techniques. Right, so look at this. Say we had to expand and simplify x plus 2. This time around, not plus 1, plus 2 to the power 5 in descending powers of x. Notice I have highlighted the word descending. Now, all the multiplications we have been doing, all the expansions we've been doing thus far have been in descending powers. So I want to keep that train. When we change to ascending powers, a while ago, Rebecca and I showed that we move from 10 to 9 all the way to x to the power 0. So we descend. You could ascend if you wanted to, and we'll get to that. But this time around, we're not expanding x plus 1. The second term in the binomial has been changed from 1 to 2. How do we do it? And that is where Pascal's triangle and other techniques come in handy. So look at this. This is how we expand it. You would notice that because the power is 5, I have done a number of things. Now, please watch carefully. And if you understand this, at least from the power 0 to 10, if you're able to memorize the coefficients and those 1, 1, 5, 5, 10, 10, or 1, 1, 10, 10 that we kept talking about are the coefficients. If you remember the coefficients, you could just plug them in and do a number of things, and I'll show you. So we have x plus 2 to the power 5. And the question says to expand and simplify in descending powers of x. Now, so we're going to expand. What did we do? We have 1. We have 5, 10, 10, 5, and 1. What do they represent? They represent the coefficients as we obtain them in Pascal's triangle. So for example, if we had x plus 2 to the power 4, our coefficients would have been 1, 4, 6, 4, 1. If we had to the power 6, we would have had 1, 6, 15, 20, 15, 6, 1. So you could first of all write the coefficients as I have done. Then we're going to do a number of things. So watch carefully. Look at the binomial. The binomial is x plus 2. Now, x is positive. Ordinarily, we would not write plus x. We will simply write x. I have taken the liberty to write plus x because the sign before the number is not always positive. And this is a usual tripping point for students. Because you are used to positive numbers, the moment a negative number is introduced, you somehow assume that it doesn't count, and negative numbers are very troublesome. Please do not omit them. I have written plus x. You could avoid writing the plus x. You could omit it, and you'll be fine because it is positive. However, I have written positive x just to remind you that the sign is important. I've also written plus 2 or positive 2 to also remind you. I want you to keep reminded Recall I said early on in the show that we are particular about details in mathematics. And this show is to show you specific points to avoid as you enter into the exams. You may have done it so many times and be pardoned. You would not be pardoned in the final exams. It's critical. So we have 1, 5, 10, 10, 5, 1 written out. You could write them out with spaces. And then plus x plus 2. Each time I've written plus x plus 2. For each case, notice they are repeated. Plus x plus 2. Plus x plus 2. All the way to the very last, where we have 1, then in parentheses plus x, and then plus 2. But something is going to change because the instruction is to expand and simplify in descending powers of x. We will do this. Where you have x, because it's in descending powers, descending means you're starting from the highest to the lowest. So like you're descending a staircase. You are descending a ladder. You are descending means you're on a height, you're coming low. So the highest is where you begin. The highest in this case is 5 because the highest power is 5. So I put x as 5, x as 4, x as 3, x as 2, x as 1, and x as 0. So I have descended from 5 to 0. Now, the moment I do that, I have to do something else. You notice I have concentrated on the first term x. The second term, which is plus 2 or positive 2, I have to make sure that the powers, when added, will still give me 5. In other words, since I have 5 here, what do I add to 5 to get 5? 0. Now I have 4 here. What do I add to 4 to get 5? That is 1. And I have 3. What do I add to 3 to get 5? That is 2. And on and on and on. In other words, the moment you feed in the first, that is the powers of x, 5, 4, 3, 2, 1, 0, you can now even start from the end and begin 5, 4, 3, 2, 1 for the other term. In this case, our term is positive 2. When you have done that, you're pretty much done, except to really expand. So if we expand, this is what we have. Now notice very carefully that the powers have been put outside of the parentheses. Please do not put them in. Do not put them within the parentheses. Don't put them in the bracket. If you do, there's a temptation to do certain wrong things. That is another tripping point for students. You think it doesn't count? It does count, especially if the term, the second term you're dealing with, is a two-term thing. So for example, let's say you had 2x. If you put the power inside, it will assume it as 2x to the power 5, when in reality what you meant to say was 2x all to the power 5. It's another tripping point. So always put the powers, the exponents, or the indices outside of the bracket or the parentheses. So when you have done what is outside and you have already expanded, then you can come inside like you have on this next line. So when we expand, we have x to the power 5, 1, x to the power 4, and on and on. Now in the last case, we have, or just before then, here we have positive 2 to the power 2. That gives us 4, which we have here. Positive 2 to the power 3, we have 8. Positive 2 to the power 4, we have 16. And positive 2 to the power 5, we have 32. So now we have that expression or that equation, that side of the equation over there. Now we need to tidy it up. If you tidy it up, we have 1 multiplied by x to the power 5 multiplied by 1 gives us x to the power 5. 5x to the power 5 multiplied by x to the power 4 multiplied by 2. 5 by 2 gives us 10. So we have 10x to the power 4. 10 multiplied by 4 multiplied by x to the power 3. We have 40x to the power 3 and on until we get to 1 multiplied by 1 multiplied by 32, which gives us 32. So you notice that using the coefficients as produced by Pascal's triangle, we are able to expand x plus 2, not x plus 1 this time around, x plus 2 to the power 5. We could have expanded anything, and I'll show you a few more examples. So this is how to use the Pascal's triangle. So if your question comes in this manner, using the Pascal's triangle, expand and simplify in descending powers of x, so and so, this is how to go about it. Let's try another example. We have x minus 2 to the power 5 to expand and simplify in descending powers of x. Notice something curious. This time around, it is not x plus 2. It is x minus 2. Note that, minus. So how do we operate? The same thing we did the last time. The difference though is that this time around, you are not going to have positive 2, you're going to have negative 2. So it will look like this. So wherever there was a positive 2, it changes to negative 2. And the expansion will go on like previously. So we're going to have that. So negative 2 to the power 0, 1. Negative 2 to the power 1, negative 2. Negative 2 to the power 2, 4, because negative 2 multiplied by negative 2 is positive 4. If you're using a calculator at this point, caution. If you're going to use negative 2 to the power 2, you must put it in parentheses, else your calculator would likely return the answer negative 4, which would be wrong. So negative 2 all squared on your calculator, if you're going to use that, or anything to the powers, if what you are expounding is a negative value, please put them in parentheses, put them in brackets on your calculator, else the answer it will return will be negative, which is wrong. So negative 2 all to the power 2 will give us positive 4. Negative 2 to the power 3 will give us negative 8. Negative 2 to the power 4 gives us positive 16. And negative 2 to the power 5 gives us negative 32. If we expand that line further, we return the value x to the power 5 minus 10x to the power 4 all the way to negative 32. So you notice that so long as you know the coefficients of the Pascal's expansion for any power, you could just place the coefficients there, put in the terms, and follow the instruction, descending, ascending. If it's descending, you start with the highest power for whatever variable it is, x or y or a or b or c, whatever, and keep reducing until you get to 0. All right, a third example on this. This time around, we have to expand and simplify negative x minus 2 to the power 5 in ascending powers of x. No longer descending, now ascending, no longer x plus 1 or x plus 2 or x minus 2. Now it is negative x minus 2. So this time around, both terms of the binomial are negatives. What are you going to do? Practically the same thing, except to take note of a few things. So we have 1, 5, 10, 10, 5, 1. And I'm referring to 1, 5, 10, 10, 5, 1. You write the coefficients. And then the terms, negative x, negative 2, negative x, negative 2. But this time around, the instruction says in ascending powers of x. Ascending means you're moving from the lowest to the highest. The highest is 5, the lowest has to be 0. So I start with x to the power 0 and x to the power 1 and x to the power 2 and 3 and 4 and 5. And then I reverse the process for negative 2. So I start from the end, 0, 1, 2, 3, 4, 5. In each case, when I add the powers for negative x and negative 2, I should have 5. So 0 plus 5, 5, 1 plus 4, 5, 2 plus 3, 5, 3 plus 2, 5, 4 plus 1, 5, and 5 plus 0, 5. This time around, I have expanded negative x, or the binomial negative x minus 2 to the power 5 in ascending powers of x. I have ascended. Previously, we descended. Now, we have ascended. All right. And if we went on to do that, we should have something that looks like this. And our final answer should be negative 32 minus 80x minus 80x squared minus 40x to the power 3 minus 10x to the power 4 minus x to the power 5. You notice this time around, the x to the power 5 is at the last point. It's at the end because it was in ascending powers of x. And those are the things we look out for. Please do not do an autopilot of things. Be very careful with the instructions. They are very important to us as mathematicians. Ascending powers, do not solve it as descending powers. You lose marks for that. The result may be the same in terms of value, but you have disobeyed the rule and you get punished for that. All right, so this is how to use the Pascal's triangle in expansion of any binomial. We're going to look at other techniques, and that will bring us to an important concept, the factorial. The factorial, what is it all about? Now, why do we even need the factorial? Well, the factorial by definition is the multiplication of any number, rational number, whole number, until you get to 1. That is one way of defining it. So if we have any whole number, positive whole number that is, and we multiply in descending order until we get to 1, we call it a factorial. A few examples on your screen. You have 3 factorial. We have 3 factorial, 4 factorial, 5 factorial, all the way to n factorial. Now, watch it. 3 factorial is 3 multiplied by 2 multiplied by 1. 4 factorial, and that exclamation mark is our notation for factorial. So we call it factorial. So 3 factorial, 3 multiplied by 2 multiplied by 1. 4 factorial, 4 multiplied by 3 multiplied by 2 multiplied by 1. 5 factorial, 5 multiplied by 4 by 3 by 2 by 1. If I said 8 factorial, it should give you the same thing, 8 multiplied by 7 by 6 multiplied by 5 multiplied by 4 multiplied by 3 multiplied by 2 multiplied by 1. So for any number n, if you're going to multiply, you just multiply, so long as the number is a positive number, it's going to be n multiplied by 1 less than that number, n minus 1, multiplied by 2 less than the original number, n minus 2, until you get to 1. So let's put 9 in the place of n. It will be 9 multiplied by 9 minus 1, which is 8, multiplied by 9 minus 2, which is 7, multiplied by 9 minus 3, which is 6, until we get to 1. But something to quickly note, that 1 factorial is equal to 0 factorial, and both of them have the same value, 1. On your calculator, the factorial is a second function. So depending on the calculator you're using, if you typed in 4, for example, shift, you will need to look at the keys and which of them has the exclamation mark. Depending on the calculator you're using, it will be located differently. But if you did 4 shift the factorial, your answer returned on your calculator screen should be 24. 3 shift factorial should return 6. 5 shift factorial should return 120. And on and on. So that is the factorial. And I want you to try your hands on a few of them and get yourself used to them. How do we use the factorial? I shall show you one example, and then we shall go for a break. And I hope that in the course of the break, you will be able to try your hands. So let's look at this. The second concept, why we use the factorial, is the combination. Now, we write it in two different ways. So we could have a parenthesis and write n, and below it r. Please, there is no line in between them, as though you're writing a fraction. It's as though you are writing a vector. So n, r, it is said r, choosing r from n. Or the second way to write it, n, cr, is read n combination r. In other words, we have n total items and we are choosing r of them. So for example, if we had 10 items and we're going to choose 4 out of them, we will say 10 combination 4. That is just in how many ways can we choose 4 items out of 10. So we have 10 people in a room and we wanted 4 of them to be taken on an adventure to a park. Or you have 10 people but you have money enough to feed 4. Which of the 4 are you going to pick if you didn't want to be biased? Well, there are many combinations of that. So it is taking 4 out of 10. That is what this simply means. Well, you get to meet this concept again when you're treating probabilities. We're going to use the factorial in this case. So watch how it works. So if I say n combination r, it simply means n factorial divided by n minus r, all of that, the result of that factorial, multiplied by r factorial. I'll take it again. N combination r will be n factorial divided by n minus r, or factorial, multiplied by r factorial. So if we had 6 combination 2, it will mean 6 factorial divided by 6 minus 2 factorial, 2 factorial. The catch here is whenever you add the denominator, you should have the numerator. So if we evaluated this further, we would have 6 factorial on 4 factorial multiplied by 2 factorial. Why do we use this? Why do we need to learn this as concept? It's because in trying to expand powers of any binomial, sometimes they get pretty large or pretty small. And we need to find a way to deal with them without having to use Pascal, because Pascal's coefficients and triangles have a limitation. At some point, we can no longer use Pascal. We need to find a quick way, an easier way to resolve this. When we come back from the break, we shall delve into how to use this very powerful tool of the factorial and combination to solve binomial expansions. I'll see you after the break.
The time is up for the Joy Learning Revision Show. The time is up for our dear final year senior high school learners to start preparing for their final year WASI. And as always, our TV teachers are ever ready to take you through your revision sessions on Ghana's first ever educational TV channel, Joy Learning.
Presenting to you word problems in mathematics.
The SHS Revision Show is coming with a new segment called The Question of the Day, and students who will answer the specific subject questions correctly will be rewarded. Dear final year learners, don't be left out of this year's SHS Revision Show every Monday to Friday at 7:30 p.m. And remember to tell a friend that the time is up for the revision show.
As sellers are going into the market, the profit margins will be falling.
Starting on Monday, 13th June 2022 at 7:30 p.m. Joy Learning, keep learning. The rainy season is here again. In the major cities of Ghana, flooding has become the key source of human vulnerability, and varied attributions have been given to its frequent occurrences. Dear learners, it's time to show off your writing skills on the Joy Learning Essay Club contest. In not less than 300 words, write on the topic, what can be done to prevent perennial flooding in Ghana's major cities? Your essays must have your full name, your age, your contact, and your school's name. Send a copy of your essays to Facebook at Joy Learning TV. You can also email to joylearningtv@myjoyonline.com or drop off at the front desk of Multi TV office. The best 10 essays qualify to be part of the finalists of this educative contest, and there are so much Joy Learning branded items to be won. Not forgetting the opportunity to become a Joy Learning ambassador for 2022. Remember, the topic is what can be done to prevent perennial flooding in Ghana's major cities, and the deadline for submission is Friday, 24th June 2022. Joy Learning Essay Club, improving our writing skills and sharing our thoughts on national issues. Joy Learning, keep learning.
You're welcome back. This is your Joy Learning channel, and you're onto the revision show. Tonight, I am your guide, leading you through elective math for especially those of you writing your final year exams shortly. Before we left for the break, we were able to see a few concepts with binomial theorem. We saw that you could use the Pascal's triangle of coefficients to resolve any expansion so long as the powers were positive. Well, we introduced the concept of the factorial, which would require that you multiply any number in decreasing order until you got to 1. And we said as a special note that 1 factorial as well as 0 factorial, where factorial is a mathematical way of saying multiply downwards, 1 factorial and 0 factorial all give us the value 1. Well, let's not argue about the 0 factorial thing. Let's use it for now. Later we can resolve that. Well, we said also that there is another concept called combination, more like picking some items out of many items, and we're asking in how many ways can that be done? Well, we're using both concepts in place of Pascal, and we got to the point where we said 6 combination 2, for example, will yield us 6 factorial on 4 factorial 2 factorial. Let's complete that process. So if we evaluated it further, 6 factorial will be 6 multiplied by 5 multiplied by 4 multiplied by 3 all the way to 1. 4 factorial, which is the first element in the denominator, will follow the same pattern, 4 by 3 by 2 by 1, and then 2 factorial will be 2 multiplied by 1. Now, if we tried our division, you would notice that 4, 3, 2, 1 will take out 4, 3, 2, 1. So we'll end up with 6 times 5. Now, sometimes it is useful not to write everything, because sometimes it could get pretty long. So instead of writing 6 by 5 by 4 by 3 by 2 by 1, you could simply write, noting that in the denominator you have 4 factorial, you could simply write 6 by 5 by 4 factorial. Why? Because if we kept on writing the 4 factorial, it would have been 4 times 3 times 2 times 1, which will be a repetition of something in the denominator, which will be needless because eventually they will be cancelled out, like you can see on your screen. So we have 6 by 5 by 4 factorial instead of writing 4 by 3 by 2 by 1, etc. And this time around, if we're going to divide, all we needed to do was to strike out 4 factorial, which divides 4 factorial. So you end up having 6 by 5 divided by 2 by 1, in which case 2 will take out 2 one time and take out 6 3 times. So we end up having 3 times 5 divided by 1, which gives us 15. So 6 combination 2 is 15. How does all of this show up in binomial expansion or binomial theorem? Watch this. Recall that x plus 1 to the power 5 give us the answer you see on your screen. What if we chose to use the combination? What would it look like? It will look this way. In place of the 1, 5, 10, 10, 5, 1, we could have simply written choosing nothing from 5, or 1 from 5, 2 from 5, 3 from 5, 4 from 5, and 5 from 5. And we would evaluate it as we did just a while ago. So we'll evaluate the coefficients this way. So that is another notation. Instead of 5, 0, we could write 5 combination 0. And if we evaluated it, we would have this. 5 combination 0 will be 1. 5 combination 1 will be 5. 5 combination 2 will be 10. 5 combination 3 will also be 10. 5 combination 4 will be 5. And 5 combination 5 will be 1. You notice to the extreme right of each of those evaluated combinations, we have values in red. 1, 5, 10, 10, 5, 1. Did you notice that it is the same as what Pascal had when we use the Pascal's triangle? In other words, if we intended to expand, we could just do this. In place of Pascal, so if you had a very large number, say x plus 1 to the power 20, instead of building a very humongous Pascal's triangle, all you needed to do was to write 20 combination 0 for the first, 20 combination 1, 20 combination 2, until you got to 20 combination 20. And you'll be fine. So again, it will look like this. And then we can now apply it. So in general, and please, you could write this out if you do not already know it. In general, a very important formula to have handy. Copy it into your notebook. In general, a plus x exponent n will be a exponent n plus n combination 1 multiplying a exponent n minus 1 multiplying x exponent 1 plus n combination 2 a exponent n minus 2 x exponent 2 until you go to x exponent n. Now, I want you to notice this. A few things. Number one, a is not just an alphabet, it's a placeholder. In other words, so long as the value is not x. So if I had 3 plus x to the power something, the 3 becomes a. And x is x. Indeed, x is not just x. If I said 3 plus 2x to the power 7, my a is 3. My x is not just x, it is 3x, because that x is not just x as an alphabet, it's a placeholder. And my n in this case will be 7. Now, look at the right side of the expansion, which is actually below on your screen. You would have, beneath x plus x to the power n, you have a to the power n. Truly and really, there should have been an n combination 0. so that we have it complete. Combination 0, combination 1, 2, 3, all the way to the end. Well, we don't write it because it will still yield 1 at the end. Now, let's look at how this is formed. So here, we are dealing with this in ascending powers of x, if you notice. So there is no value of x here, so it is 0. To the power x 1. Here, x is to the power 2, to the power 3. Note, I'm referring to x. X all the way to the power n, because the highest power is n. So we're dealing in ascending powers of x in this case. Now, watch again. You would notice that the first power of a is n minus 1. The second is n minus 2, n minus 3, on and on and on. Now, you would notice also that if you added the powers, so for example, if you added n minus 1, if you added it to 1, you would have n minus 1 plus 1, which would be n. So in each case, every time you add the powers, you must get the original power you were working with. And it is not very confusing, a formula. Always remember that you are dealing in ascending powers. Actually, you could make it descending if you wanted. In that case, you have to reverse a few things. So you have n combination 1, n minus 1, n combination 2, n minus 2, n combination 3, n minus 3, all the way down. Now the powers for n increase from 0, the first case, to 1, 2, 3, on and on. So that is a general formula. Please note it, we'll use it quite a bit. Then, if you expanded it, then it will look like this. But you don't need to bother about this expansion. If you are interested, n combination 1 will be what you see in the first case here. Because n combination 1 will simply give you 1. I mean, it will give you n, I beg your pardon, not 1. And then n combination 2 will be n minus 1. Remember what we said? That anything, 3 factorial will be 3 multiplied by 2 multiplied by 1. So n combination 1 will be n factorial divided by n minus 1 factorial, 1 factorial. So n combination 2 will be something on 2 factorial. That something will be n multiplied by n minus 1. And you notice we have x squared. Again, I need to emphasize, and it bears repetition. Please, the a and the x are not values in themselves. They only tell you the placeholder. All right. Now, all of this, let's use it and see how it works. 2 plus 3x to the power 5. We are required to expand and simplify. 2 plus 3x to the power 5. What would it look like? We're going to use the general term. So in this case, what is a? A will be 2. What will x be? It will not just be x. It will be positive 3x. Again, you could have written 3x, but I am taking the liberty to write positive 3x because I want you to remember that when it is negative, don't ignore it. So, and I'm beginning from 5. So n is 5. It drops to 5 minus 1, 5 minus 2, until we get to 5 minus 5. The powers of x increase from 0 to 1 all the way to 5 at the end. So if we do a further expansion, we have positive 2 in there, plus 3x, all replicated. And since it's an ascending powers of x is 1 there, x is 2, x is 3, x is 5 at the end. If you added the powers, 4 plus 1, 5, 3 plus 2, 5, 2 plus 3, 5, and on and on. And look at the combinations. Combination 1, combination 2, all the way to 5. Pretty straightforward. So let's expand it. So we have 2 to the power 5, 32, plus 5 combination 1 is 5. 2 to the power 4, 16. Positive 3x to the power 1, 3x. 5 combination 2, 10. You recall 1, 5, 10, 10, 5, 1. Alright, so 10, 2 to the power 3, 8. Positive 3x to the power 2, 9x squared. Reason you should not put the squared inside the parentheses. If you do, you will read it as 3x squared, which will be wrong. It is 3x all to the power 2. In other words, positive 3x multiplied by positive 3x. In the third case, 5 combination 3 gives us 10 as well. 2 to the power 2 gives us 4. Positive 3x to the power 3 gives us 27x to the power 3, because it is positive 3x multiplied by positive 3x multiplied by positive 3x. And all the way till we get to the end. And when we do all of that, 2 plus 3x to the power 5 will give us 32 plus 240x plus 720x squared plus 540x cubed plus 810x to the power 4 plus 243x to the power 5. In this case, x has been expanded in ascending powers. Now we are no longer dealing with x plus 1. We're now dealing with 2 plus 3x. Remember, a and x are not the values themselves. They just hold a place. They just show us that in that location, whatever is there, call it a. In the other location, whatever is there, call it x. So instead of a, we have 2. Instead of x, we have 3x. Please do not leave out the 3, the coefficient, if it has 1. And do not leave out the sign. If it's positive, you may go scot-free. If it is negative, it will be disastrous. Well, now we know that a plus x to the power n gives us this. It can be written in a shorter version, in a shorter form. So we could write a plus x to the power n as, now you're familiar with that symbol. It is called sigma, a Greek alphabet sigma, capital sigma. And this is sigma of a value 0 to the power n for the general expression n combination r, a to the power n minus r, x exponent r. Of course, n combination r can be written as nr, choosing r from n, an alternative way of writing the same thing. Okay, so let's try expanding something slightly different. This time around, negative 3x, just to show you that the negative sign is important. So if we use this notation, it will look like this. We would have 5 combination r, where r is any number from 0 to 5, because our highest power is 5, so we start from 0. And then a is 2 from the question. Our x is negative 3x, not just x, negative 3x, and not just 3x, negative 3x. And so we just use the notation where n is 5, so we have 5, and then r is r. R could assume any value from 0 to 5, so long as it's a whole number. So we could have 0, 1, 2, 3, 4, and 5. So we have 5 combination r, 2 to the power 5 minus r, multiplying negative 3x to the power r. Now remember, it says sigma, which means summation. It's a symbol you have met quite a lot of times, especially in statistics. It just tells us that keep adding. It's a summation symbol. So it means when we start with r as 0, we add to whatever value we get to that, r to the power 1. All right. And we keep going on and on. All right. I have a caller who has a question. Good evening. Who do I have on the line?
Steven, my name is Ernest.
Yes, who do I have on the line?
Ernest.
Ernest, good evening. So Ernest, you have a question. May I hear you, please?
Please, I wanted to know the value of r.
Oh, you wanted to know the value of r?
Yeah.
Okay. I would respond to that as we go on, if you don't mind.
Okay.
Is that okay?
Okay. Yes.
All right. So Ernest is asking, what is the value of r? Now, remember that we said that n combination r is n factorial So I'll write it somewhere here. We said n combination r is equal to n factorial divided by, in parentheses, n minus r, or factorial multiplied by r factorial. Now that r is an arbitrary number just like n, but often r, not often, all the time, r cannot be greater than n, never. It must always be less, and it has to be a whole number or zero. I mean a positive number or zero. So for example, if we had 6 combination 2, 2 in this case would be our r. So r is any number you are evaluating. That's why for the general term here we said r is equal to 0 all the way to r equals to n. So in the specific example of 2 minus 3x all to the power 5, r will begin from 0 and travel all the way to 5. So r in this case will be 0, 1, 2, 3, 4, and 5. If you want to call it a set, then you can do that. So r will assume all of these values, not any actually, in this case all of it, from 0 to 5. So 0, 1, 2, 3, 4, 5. So when you put r as 0 in the first case, you have 5 combination 0, multiplying 2 to the power 5 minus 0, multiplying negative 3x to the power 0. You get a certain value there. Then you add it. Why are we adding? Because of the symbol sigma. It says add. Then you come again. 5 combination 1. We've finished with 0, so we are now on 1. 2 multiplied by 5 minus 1. Negative 3x multiplied by 1. Plus 5 combination 2. Multiplying 2, 5 minus 2, negative 3x to the power 2, plus we continue until we get to 5 combination 5. So you notice that r would assume the values you give it based on the range of values you were working with. By the way, it is not always r. Some textbooks and some teachers prefer different alphabets like K. So you could see K0 to N. The alphabet is not really that important. It just tells you your starting point and your ending point. In this case, N is our ending point, R is our discrete values we shall be picking. So this is another way of writing the binomial expansion. There is a third way. I hope you are taking note of it. So the first one we said a plus x to the power n equals to a to the power n plus n combination 1 a to the power n minus 1 x to the power 1 plus n combination 2 a to the power n minus 2 x to the power 2 plus n combination 3 a raised to the power n minus 3 x to the power 3, etc. all the way to x raised to the power n. This is the second one, where we say sigma of the whatever function it is, a n combination r a exponent n minus r x exponent r from r equals to 0 all the way to r equals x exponent r. That. Please note that. That's the second one. There is a third one. So in this case, we would have expanded that way. Now, we can write a plus x to the power n in a factored way. What do we mean by factored way? Instead of having a within the parentheses, we want to have it outside. In other words, we'll factor out a. If we factor out a divided by a will give us 1. X divided by a will give us x on a. However, when you factor the a out, you must also raise it to the power of the original binomial expansion. In this case, the expansion was to the power n. So we have a to the power n multiplying the expression 1 plus x on a all to the power n. Somebody might be asking, why do we have to raise a to the power n again? Well, the truth is, if you do not do that, it will not be the same as what you had originally. And I like it when students try to query these things. It's good. It means you're thinking. Well, try it. Try expanding any number or any binomial, say 4 plus x to the power 3, and factor out the 4 so that you have, so in this case, for example, if we had 4 plus x to the power 3, if you tried factoring it out and you had 1 plus x on 4 to the power 3, if you tried doing this, I assure you they would not be equal. They will only be equal if this 4 is also raised to the power 3 and then multiply by 1 plus x on 4 to the power 3. Only then would that be equal to 4 plus x to the power 3. And we can test it very quickly. So, for example, let's put x as, say, 1. 4 plus 1 will be 5. 5 to the power 3 will give us 125. What if we factored it? We would have 4 out in the first case, plus 1 on 4. So we have 1 plus 1 on 4. That will give us 5 on 4. 5 on 4 to the power 3 will give us 125 on 16. If we use the first instant, 125 on 16 multiplied by 4, we'll have 125 on 4. Sorry, did I say 16? 64. So 125 on 64 multiplied by 4 will give us 125 on maybe 16, which is not the answer because recall we had 125. If we use the third case, we would have 64 multiplied by 125 on 64. And 64 will strike out 64, we'll end up with 125. And that's the reason the a on the outside must be raised to the power of the original expansion, in this case n. All right, so if we did it that way, then we have a third formula you could work with, which is 1 plus x to the power n being equal to 1 plus nx plus n multiplying n minus 1 on 2 factorial downwards. You must be familiar with this if you have treated this topic. It's a very popular one. Now, this is true for n belonging to any set of rational numbers, and x must be between -1 and 1, with -1 inclusive, but 1 not inclusive. All right, so we have our three formulas. And if we're using the expansion and we have a power, if you notice, so far we have not worked with powers that are not whole numbers. But we could have a fraction, in which case we have, say, 1 plus x to the power a on b, where a on b could be any fraction, especially if it's positive. We could use a -1, of course. So let's say we have 1 plus x raised to the power half. It will be 1 plus half x plus half multiplied by 1/2 minus 1 on 2 factorial multiplied by x squared. And please recall, the x is just a placeholder. It doesn't mean x as in the value x. It just means that whatever is in that location, put it there as x, in place of x. So we have it running through that way. All right. Let's expand, for example, 2 minus 3x to the power 5 using that. If we did, it will look like this. Again, we're only just rewriting our formulas. So we have 2 to the power 5 out. When we factor 2, we have 1 plus 3 on 2. So I factored this, 2 divided by 2, 1. -3 divided by 2, -3 on 2x. And then I have my 2 to the power 5 outside here. Then I expand what I have in here using this process. So I have 1, n is 5, so 5, x is -3 over 2x. Remember, it's not just x. Plus n, which is 5, n minus 1, 5 minus 1 on 2 factorial. If you're wondering where the 2 factorial came from, remember n combination 2. So the first was n combination 0, n combination 1, n combination 2. Multiplying x squared. In this case, our x is negative 3 on 2x all squared. Plus n minus 1, n minus 2 on 3 factorial. 5 minus 1, 5 minus 2 on 3 factorial. And here there ought to be a cubed. Yep, that was missing. And we go on and on like that. So you could expand and have, of course, your cubed as well there. And you could evaluate it further. This is just to show you how it works. All right. So let's take a very definite example. Here we're going to solve a practical problem like the problem of the day. And if you're ready with your answer for the problem of the day, you may now call in. Our phone lines to be activated: 0302 211 705, 0302 211 706. We had 2 problems for the day. Any one of them, I'll take your answer. I'll declare the winner at some point in the show, and hopefully somebody is going to go away with something interesting. Trust me. Now, use the expansion of 1 minus 4x to the power 6 to find the value of 0.96 correct to 4 significant figures. So we have to do a number of things. First, we're going to have to expand 1 minus 4x to the power 6. When we are done, the question requires that we find the value of 0.96. And there's a third thing to do. We correct whatever value we get to 4 significant figures. 3 requirements. There is an expansion, there is an evaluation, there is an approximation. 3 things: an expansion, an evaluation, and an approximation. Let's begin. Our solution. Yes, I have somebody from Guinea calling me. Good evening.
Evening.
Yes, who do I have on the line?
Please, Asari Boatin Samuel.
You are Samuel. You're calling from?
Please, Kedi.
You're calling from Kedi?
Yes, please.
Okay, so Samuel from Kedi, what do you want to tell us? You have an answer to a question?
Yes, please.
Okay, which of them?
Please, the problem of the day.
All right. What was your answer?
So, please, for the first one, I had my answer to be 1 plus 12x plus 66x squared plus 220x cubed plus 495x raised to the power 4.
Can you take the answers one more time? Let's be sure.
Okay. Please, the first question.
Yeah.
Which is expanding the... Which is the first question.
Yes.
Ascending order in 5th term. I had 1 plus 12x plus 66x squared.
Okay.
Plus 220x cubed.
Okay.
Plus 495 raised to the power 4.
All right. That was your answer to the first part. Do you have an answer to the second part?
And also to the second part, which is 1 plus x to the power 12 in. Sorry, the second part, which is 1 minus x raised to the power half.
Yes.
Okay, please, I solved 3. I couldn't solve the problem, the one containing the percentage and this one. So I solved 3 out of the 4 questions.
That is great. That is great.
1 minus x raised to the power half. That's the answer for that one. So I had 1 minus half x.
Okay.
Minus 1 over 8x squared.
Okay.
Minus 1 over 6x cubed.
Okay.
Minus 5 over 128x raised to the power 4. That is the value. And then, since they said we should use the square root of 15 to correct to 3 decimal places.
Okay.
For that one, I had my value to be, when I filled in x, I equated 1 minus x is equal to 1 minus 1 over 16. The reason why I did 1 over 16 because root of 15, you can also represent it by subtracting 1 over 16 from 1.
Okay.
So I had 1 minus x is equal to 1 minus 1 over 16. And then I had x value to be 0.0625. So I substituted into the value I had for the 1 minus x raised to the power half. And then you get 0.968246. And then to four significant figures will be 9682.00.
Samuel, thank you for that powerful try. What school do you attend, if I may ask?
Please, I attend Pope John's Senior High.
Fantastic. Pojoba. That is great. So we'll find out if you're correct, Samuel. So please keep watching the show. Let's grind on. Is that okay, Samuel? Thank you very much, Samuel. So Samuel gave a shot to the question. He confesses there are some parts of the question he couldn't resolve. Maybe, Samuel, if you watch this, you'll be able to resolve that part. All right. So, Eric, good evening.
He's fine.
Good evening, Eric. Oh, I lost Eric. All right, Eric, sorry for that. So if we expand this like we would normally do, after expanding, we have what we have on your screen. We have 1 plus n, which is 6. X is negative 4x plus nx, which is 6 multiplied by 5 on 2 factorial multiplied by negative 4 raised to the power 2, on and on and on. We end up with something that looks like this. Now, this is quite longish, but our final answer, or our value before the n, looks like that, a little neater. And our final answer will be 1 minus 24x plus 240x minus 1280x cubed plus 3840x to the power 4 minus 6144x to the power 5 plus 4096x to the power 6. Now, the first part has been done. We have expanded. And the question says expand. So we have done that first part. So you get your full marks for that. Then it says to evaluate. So let's call our expansion equation 1. Now we're going to do something to it, and that's something Samuel did. Now the question says to use that expansion to find the value of 0.96 to the power 6. Now 0.96 can be rewritten as 1 minus 0.04. Where did I get that 0.04 from? It's very simple. Just recall that if 1 minus 4x is equal to 0.96, you can simply write 1 minus 4x is equal to 0.96. If you do a change of subject, or you make x the subject if you like, then you will have 1 minus 0.96 is equal to 4x. Now 1 minus 0.96 will give you 0.04, and that is where I get my 0.04 from. Just that simple. Of course, x will be of a different value. All right, so I have 1 minus 0.04, which gives me 0.96 effectively. Therefore, 0.96 to the power 6 can be written as 1 minus 0.04 to the power 6. Well, if that is so, I will just compare. Since this is the same as this, then 1 minus 4x, we can say 1 is the same thing as 1. In other words, negative 4x. And please, you notice I have repeated the sign. It's deliberate. Negatives are troublesome. If you ignore them, you'll be punished. Negative 4x is equal to negative 0.04. Hello, do I have a call on the line? All right. So it will mean that x is 0.01. Now, what am I going to do with this? I'm going to substitute that into equation 1. That's all I'm going to do. So wherever I find x in equation 1, I'll put 0.01. That's all I'm going to do. That is where a calculator comes in handy. So by substituting, I have 1 minus 24 multiplied by 0.01 plus 240. Instead of x squared, I have 0.01 squared minus 1280. Instead of x cubed, I have 0.01 to the power 3. On and on. If you did that carefully, and notice the word carefully, if you're a little careless about it, your value will be wrong. So be careful. You will get something like that. Often, the values are truncated, but I prefer to have it in full so that you appreciate it. Don't try memorizing the numbers on the screen. It's just to let you understand that this is how it's to be presented. And when you have evaluated it carefully, you should have something that looks like this: 0.7827577896. Remember, the last part of the question says to leave your number in significant figures. In other words, 0.96 evaluated will give us approximately 0.7828 to 4 significant figures. Now, if you tried with your calculator 0.96 to the power 6, you will get something very much like this. And so that is how to work. So we use binomial expansions to approximate values, like our problem for the day, which Samuel has courageously tackled. We'll check out if he's right or wrong. So this is one way of doing it. That is, first of all, you expand the binomial, equate what you have to the value you intend to approximate. You will get a certain value for x. When you get the value for x, reintroduce it into your expansion. When you do, evaluate carefully, and if you have to round off to some decimal place or significant figure, you can do so. So, a very typical example. All right. These are typical questions in your WASI. Very typical questions. Look at the questions on the screen. When you call in, I want you to tell me, well, if you have the answer, that would be great. I'll leave it on the screen for a while. But also important to me, I want to find out, are you able to notice the differences between the questions? They look alike, but there are differences as well. The questions are nuanced. There are slight differences, although there are lots of similarities. Identifying the differences is key to being able to resolve them. So we have 5 questions on the screen. Take note of them and try them. The answers are as you would if you used any of those operators we used. Let me get to Samuel as we try to sign off for tonight. Samuel had some of the questions right, some were not so right. Now, if you're copying this on the screen or taking a screenshot, that would be great. I'll provide the answers for you. So, here are the answers. You could note them down and compare. Try solving to see if you are right. Now, Samuel, you got some of it right, but your evaluation wasn't so right. So, for example, square root of 15, you decided to write 1 minus 1 on 16. That was quite smart. It could have been 16 minus 1, which would have been 15, and you could have rewritten 16 minus 1, of course, to the power whatever it was, by bringing the 16 out, factoring it, so that you have in the parenthesis 1, and then on the other side, something on 16 to another power. What you failed to do was to multiply the 16 to the power half, which should have been 4. So I'll quickly run to the solution for that so that you see how it looks like as we sign off. So this was the problem of the day. You expand, you get your expansion right. P was 50,000, which is the principal. R is 7 years, N is 12. You put them in, and your final answer is 113,000, and you are resolved on that. The second one, this is what Samuel you did. Oh, sorry, this is still the first one. So you have 113,000 cedis to the nearest thousand. This is the second one. You expanded, and your solution should have been something like this. You have this, you got this almost right. And if you expanded this, this is what it should look like. And so your final answer, Samuel, should have been 3.873 to 3 decimal places. So viewers, all too soon, we have come to the end of the revision on binomial theorem. You have learned how to use the Pascal's triangle, how to use the combination, how to use the general forms a plus x to the power n in its different variations. I hope that you will try your hands on the problems for the day, on the typical questions, especially the first 5, as we let you see them. Hopefully, in the coming days, we shall be meeting again, and we shall be bringing you another wonderful mathematics experience. It has been my pleasure taking you through this journey. I hope you grabbed a thing or two, and I hope that you practice quite much after this. Thanks for the pleasure of your company. I'll see you again next time. Bye.